So apologies about the delay with, so the next is a contributor talk from the University of Ghent, and moving from elemental structures to quaternary space, so it's getting more and more complex. So looking forward to the talk.
Thanks. Okay, so hello everyone. So today I want to address a bit of a more fundamental question, that is, how many materials are there left to discover? Now, why is this an important question? Well, we've all seen that we have already discovered a lot of structures, but we are greedy and we always want more. We want nice solar cell materials, new thermoelectrics, maybe a high temperature superconductor. And looking for these things is only useful if there is actually a large part of material space left to explore. And only then a lot of insight into how many intelligent species there might be in the universe, using very simple parameters. And so I'm going to try and do something similar, but for materials. Now, first, of course, if we're going to make such an equation, we should get some insight about material space. And so if we're going to make materials, we of course start from the periodic table. Let's consider the first 86 elements. The last ones are already getting pretty radioactive, so that's all you'll ever need normally. And now let's forget about crystal structures and stoichiometries and just count again how many materials you can make of this. So every combination of elements is a material. We already saw this a bit before, so if you take the combinations of 1 out of 86, you get the 86 unary elements. Binary, it's already 3,600, and ternary, we go up to 100,000. Now, we can keep going, and if you plot this, you get this graph. It starts with the 86 unaries, and it ends with the one material which has all these 86 elements. Now, what's important here is that it has a maximum, and this maximum is at around 43 elements, and that's 10 to the 25th. So if you take the total of these materials, you see that it's completely dominated by these materials with 43 elements. Now, I've never seen one of these before, so either we made some kind of grave mistake or we invented a new theory for dark matter. As you can imagine, we made a grave mistake, and that is, of course, that it costs energy to make materials. So if we combine two unaries in a melting pot, we heat them up so they dissociate to form a nice mixture. Then this binary that is formed will only be stable if the formation enthalpy is negative, so the bonds in this binary are better than those in the unary. Okay, we all know that. Very simple, and you can continue doing this. So you add an element C, and you get your ternary. Again, formation will be negative, it'll be stable, else it'll dissociate again. But now there's an important difference in that we have to take into account also the other unary phases A and B, and the two other binary phases AC and BC. And this brings us closer to this complex hull that you saw before. And so this ABC material can dissociate in any combination which makes it energetically favorable to dissociate, which gives you lots of different decomposition pathways. And the number of these decomposition pathways increases very fast as you go to more complex materials. And so you can count these. Luckily, someone else has already done this for us for this non-stoichiometry case. They are called the Bell numbers, and they look like this. And if you see for 43 elements, we have 10 to the 25th materials, but each of these materials has 10 to the 38th ways of decomposing. And that, of course, makes it very unlikely that any of these materials might ever exist. Now, we do know that unaries, binaries, ternaries, and so on exist, so the question is, how far to the right of this graph can we go before material space exhausts? This is a very difficult question to answer, so we can only look at experiments. You've seen this graph before, so a few years ago we saw that about 1,500 binaries and ternaries were discovered each year, while only about 500 quaternaries and about 200 quaternaries, and this was kind of plateauing already. So the question now is, does this mean that material space is exhausting already there, or just that people are not motivated to find these materials for finding materials' sake? especially when there are simpler materials to find. And so this brought us to start exploring quaternary space using initial calculations. Before I get to that, so let me introduce the quaternary materials that we investigated. So I won't look at the full space, it's very large. And this subspace, quaternary interface space, is quite interesting. Why? Well, first of all, it's made up of nice simple elements, the SMFP block, very nice for ab initio calculations. And so they form single phases. And these kind of combine covalent and ionic bonding in one crystal, typically by making a covalent subunit out of the P block, and then the chalcogenic species in this covalent subpart ionically bond with the elements in the S block. Okay, so now we have this space to explore, and of course it would be interesting to see what does this space look like. Sadly enough, unlike the universe, it is not three-dimensional, but you both have a compositional and a geometric space to take into account here. But still, we're going to try and make a bit of a map. So what will we do for this? We extract all the known structures from the International Crystal Structure Database. Then we remove all the ones with partial occupancies. You already heard why we do that usually. Then we're going to generate some features to generate to represent each of these materials. We'll just be using atomic features, the stoichiometry number associated, and then the space group as a geometric feature. And then we will cluster them in the high-dimensional space with this density-based algorithm, dbScan, and finally project them down onto 2 dimensions with TSNE. So that's a manifold learning method. So you take a manifold in the high-dimensional space, fit it through the points, and then pull it flat, as it were. And this gives you this map. So what we see here, effectively, the materials have been organized by their complexity because we use stoichiometry and space group as a feature. So in the top left, you have the nice simple materials, 1114 stoichiometry, for instance. And as you go to the bottom right, you get the horrible things, at least for computational scientists, with huge unit cells and very complex stoichiometries. What else do we see here? We see there are several clusters, about 25 here. Most of them only have about 5 or 6 entries. These are crystal prototypes which have different compositions tested. And there are a lot of these unique points, so these are the red points. And they are individual crystal structures. This is not unexpected because I think about 40% of quaternary structures has a unique crystal structure. So it's a big question whether these are all clusters themselves or whether they are just unique entries. But yeah, now we have a bit of a feel of what this space looks like. We can try making this rate equation. So what I'm going to say now is that estimating the number of materials based on our observed quaternary interfaces here is a bit like estimating the number of planets based on what we've seen in our own galaxy. And thus you can write down a simplified rate equation. So for the planets with life, it would be you take the number of planets divided by the number of planets in our galaxy. So this is just the number of galaxies times the number of solar systems in our galaxy times the number of observed planets for each solar system. So for instance, solar systems far away will miss the small planets, let's say. And then we must correct that with the total number of planets there should be in that solar system, because just because we don't see them doesn't mean they're not there. And then finally you can multiply this with a fraction of which planets you expect to have life. And so we can now do the same for materials. So the number of useful materials should be the number of materials in total space, in this case quaternary space, divided by the number of materials in our subspace, times the number of materials in each of these clusters, times the number of observed materials in this cluster, and then the very horrible fudge term, the number of total materials in each of these, for each of these observed materials, which of course we don't know. So this is something we're going to estimate using high throughput ab initio screening. And then finally we can multiply this with a fraction of useful materials, but since we're only interested in stable materials here, so that's just 1. If you want a superconductor, it's going to have a lot of decimals most likely. But yeah, that's not my problem at the moment. Okay, so we need to estimate that corrections factor. So here I'm going to take 3 samples in the nice part of quaternaries interval space. We're going to calculate some more samples in the future, but it's a good start. And they look like this, so they're all a bit different. The first one is a kind of layered structure with 6 known materials. The second one is a kind of sodium chloride-like structure, but with a covalently bound anion, as it were. I think there was only one known. We got it from a paper, but it was very easy to simulate, so definitely interesting to try. And then finally a more complex structure. So this is like a cationic cage with some covalently bound counter ions, which has a 6143 stoichiometry, which is already complex enough. And there were about 4 known. Okay, and then we create a database of hypothetical materials by substitution. So all the group 1 elements here get replaced by an element from the S block. All the chalcogenic species, so sulfur, selenium, tellurium, get replaced by either sulfur, selenium, or tellurium. We also looked at polonium originally, but no one's interested in polonium, and it's very difficult to get a good phase diagram, so I'll be skipping those for now. And then the remaining P block elements gets replaced by one of these 12. And then, of course, we get the number of combinations. So 3,168 for the first family, 2,000 for the second, and about 1,700 for the third. And we're going to calculate this with high throughput ab initio screening. So it's done with FASP, PV functional. We get the formation energy through this convex hull that was described earlier, which we calculate with reference to the materials project database. So that has most of the ICSD. And we automate it with our in-house software QManager. Okay, so what does the workflow look like? So we take a template structure here, this cesium lead phosphoselenide. We replace the atoms, we scale the volume a bit, then we let FASP relax the volume again, adapt the shape and the internal positions. We still do an equation of state fits to get a nice equilibrium volume, and then finally we calculate this whole energy at a bit higher setting still. Of course, doing all these calculations purely with DFT still remains quite heavy, which is why we've also started looking into machine learning. So we use a bit of surrogate modeling. So the idea is that, okay, these are very well-defined subspaces of material space, so we should be able to learn which regions are actually stable as we do the calculations. So for this we use a very simple Gaussian process model. We just take atomic information in and try to predict the whole energy. We can get away with this because we are only varying the composition in each of these, for each of these prototypes, so the geometric information is actually quite limited. And then we integrate this with our automation software to prioritize the calculations live based on the predictions of the convex hull. So in this way, it slowly biases itself towards the stable materials after any initial sampling plan, which has been defined by the surrogate modeling literature. Okay, so here's an overview of some of the variations of our Gaussian process models. Effectively, so you have here varied kernels, and then either a sampling by the most likely to be stable, or the most or the lowest energy, let's say, lowest confidence bound here of the whole energy. And effectively all perform very similar. This Matern kernel performs a bit better, but it's not sure whether it's really statistically significant, let's say. So overall, we can get about 90% of the stable materials in each of our subsets in about 300 samples, which is up to a 10-fold speed increase in the calculations. But yeah, of course, now it's the question, how many stables did we find in each family? So in the first one, we found about 108 stables, so that's 1 in 30. In the second, 116, so that's 1 in 20. And then in the third, 150, that's 1 in 8, because here we didn't calculate the entire hypothetical database. in the future we will really be using our live machine learning algorithm, but here we still calculate the entire families to get some data. Okay, so now we can try to fill in our Drake equation. So the first term we estimate by getting the information out of the ICSD. So if you look how many materials there are with decomposition, it gives 46,000 results. This of course includes some duplicates and wrong structures, let's say, but it's the best we can do without a lot of analysis. And there are about 509 in this quaternary interface, giving a factor of 90. Then the number of clusters is of course difficult because it's a very lightly explored region, but there are about 25 clusters, actual clusters, and about 75 uniques. Now it's hard to say whether this will also be clusters with a lot of materials, but I'm going to include them because we ignored both the partial occupancies, which was about 60% of this space, and there are likely a lot of crystal structures which haven't even been explored. So a factor of 100 here seems reasonable. And then on the previous slide, of course, we saw that this product of, so the number observed per cluster corrected with the total number for the observed gives you the total number for each cluster, was about 110 materials for each. So if we multiply these, then with the fraction that is useful, in our case 1, since we are just looking for stable materials, we get about a remaining 1 million materials in quaternary space, of which 47,000 are known and 500 new ones are found each year. So while this is an extremely rough estimate, it's likely that it's going to be an underestimation since there is still a lot of exploring to do. And this brings me to my conclusions. So we set out to try and answer how many materials there are left to discover using this Drake equation approach. We found about 110 new stables for each of our 3 families, which of course should be further evaluated for more of these prototypes in both quaternary simple space and out there. Using surrogate modeling, we can speed up our screening about a factor of 10. So using about 300 samples per family, and we can fully automate this with our software. And then it would seem that there are about 1 million at least remaining in this quaternary simple space, and likely you can go further towards quaternary and beyond still. But of course, further exploration is still needed, so we'll be releasing both our code and our database towards the public, and hoping that maybe some experimenters will try to synthesize them, or others will want to add to the parameters you need for this Drake equation. And so thank you for listening, and if you have questions, please ask.
Thank you very much for a really interesting talk. I'm sure there's a few questions. So let's start off with one. So you talked about interfaces, which is a big thing in solid-state chemistry.
Yeah.
And chemists have a set of rules about these interfaces where they assign formal charges to these. So when you build all these combinations of candidate materials, do you take into account some of these empirical rules, or do you just say, I combine all the...
Yeah, so in the first 2 families, we try to be quite objective, while in the third one, we take some more stoichiometry rules into account, but it's also not as easy to make this charge summation as it is for binaries or ternaries. And we also see that, for instance, in the first family, that we actually got 3 resulting geometries which were a bit different, and they all correspond to different charge stoichiometries. So it's changed a bit your screening space, and you get materials which are still stable. Yeah.
So where do you draw the line for the percentages that you include when you explore this space, the quaternary space? So oftentimes the materials that are interesting become interesting when you add like ppm amounts of other like dopants or additives.
Yeah, that's of course a good question. Here I just based myself on the results which are in the ICSD, but yeah, indeed you could consider a highly doped material still to be a quaternary as well. But yeah, of course, so what we looked at here mostly were they're still fairly small unit cells, so the biggest ones, well, there were a few with like 500 to 2,000, but most are much smaller and have very unique crystal structures which strongly depend on all four of these elements. And you will not retain them if you substitute them.
Any further questions for the moment? Now let's thank our speaker again.